Okay, our speaker is Qiantan
Let's start.
from Stanford, and the talk will be on recursive program synthesis using paramorphisms.
Right. Everyone, my presentation today is about a stochastic program synthesis project I started with Alex. We've had some remarkably exciting results to the extent that it's surprising to us that it even works. We're still exploring ways to generalize its success. For today's talk, I'll first introduce
Afraid
the
we've got no
problem and
sound
prior
for you
work.
at the moment. We're just working on it.
Those. Right, can everyone hear me now?
I'm afraid we still can't hear you.
You all can't hear me. Wait, I think in the how about now? Hello?
Could you just try saying something for a second, please?
Check.
There we go. We've got sound. Fantastic. All good. I think we're ready to go.
Okay, let's start. Hi everyone. My presentation today is about a stochastic program synthesis project I started with Alex. We've had some remarkably exciting results to the extent that it's surprising to us that it even works. We're still exploring ways to generalize its success. For today's talk, I'll first introduce the synthesis problem and prior work, talk about what we have achieved and how we achieved it. Then I'll leave some time for discussion. Now let's talk about some prior work. There has been substantial interest before in the programming by example problem. Most prior success has been focusing on domain-specific languages, in which case it's possible to develop data structure that will represent the semantics of a large class of programs. For example, synthesis systems have been developed for language with a few primitive string operations, a subset of SQL, and graphical programming languages. This synthesis system has some notable common characteristics. The task is domain-specific. The language is first order, and they do not deal with complex control flow. These systems have developed very efficient data structure and algorithm for those specialized tasks, much more efficient than exponential search in the space of programming terms. However, it's usually difficult to generalize this algorithm to general-purpose programming. It's not surprising that synthesizing general-purpose programming is much more difficult. Maybe the single most important feature that distinguishes general-purpose languages from domain-specific languages is recursion. There has been some success by limiting the scope to data transformations. For example, a recent paper employs conflict-driven cluster learning to synthesize first-order programs that uses list processing combinators. The combinators themselves, including sort, reverse, take, sum, etc., are recursive functions, but the programs to be synthesized are not explicitly recursive and rely on these combinators to perform recursive computation. One interesting instance in the space is lambda square, which uses some similar ideas as an system, including the use of high-order combinators. We include this system in our comparison. Finally, the goal of general-purpose programming synthesis is to directly synthesize recursive functions with explicit recursion. This has turned out to be difficult for deduction-based synthesizers because we might not even know the semantics of a function when we need to synthesize or call it. Early system requires so-called trace completeness to work around this issue. Basically, input-output examples have to include example for all recursive calls, which is a serious limitation. Some later systems elevated this issue, but according to our test, they are still sensitive to the choice of examples and can at most synthesize simple functions with one level of recursion. What does one level of recursion mean? For example, Smith and Trial, two of the prior state of the art, can synthesize multiplication if you provide addition as a library function, but if you provide just 0 and the successor function, this problem is out of their reach. Now, let's talk about some results. First, let's look at some numbers. We have assembled a suite of 15 synthesis benchmarks for functional programs from previous Smith benchmarks, the Haskell prelude library, and the Haskell data.list library. We tested the system on randomly generated example to test the sensitivity to the choice of examples. Across 55 out of 59 benchmarks, significantly outperforming previous systems. Notably, Para benefits significantly from parallelism. We are showing performance of Para using 8 cores in the first column and single core in the third column. Para speeds up almost superlinearly and solves more problems. This is because Para's underlying stochastic search algorithm is both embarrassingly parallel and benefits from concurrency, which is a distinct feature when comparing with previously deduction-based systems. Now let's look at some progress Para has synthesized. Our synthesizer Para can successfully synthesize significantly larger and trivial programs when comparing to prior systems. Let's look at a simple example, the factorial function. As the first assignment of many functional programming courses, it is not that complex. However, think about what if you're asking someone who don't know multiplication and addition yet, and knows only about inductive definition of natural numbers, maybe some preschool student in France. Moreover, what if you don't know what is factorial either, and you are only provided with the first few examples? You have to invent the factorial itself from inductive reasoning alone. This doesn't seem like a simple problem anymore. Here's an example of a definition of factorial using only 0 and successor. There is a significant amount of code. In any case, Para has managed to do it. Para has discovered the following program from scratch without any prior knowledge about addition and multiplication, etc. We only supplied it with successor and 0 and 6 examples, aka the value of factorial from 0 to 5. And then Para came up with everything needed to compute factorial on its own. We know that the success of Para depends on our decomposition of the program into a template colored in black and host colored in red. The template uses recursive scheme to express a quite general class of programs and is iterated in the outer loop. And we then use stochastic synthesis to synthesize non-recursive terms colored in red. More on this later. Para has shown excellent ability to come up with programs from very little prior knowledge, which is unprecedented for previous systems. Let's see a few more examples. First, it invented 3 different algorithms for list reversal. He also came up with the Fibonacci sequence, again from only successor and 0 without any knowledge about addition. Then, Para also came up with different traversal orders for trees, this time from only counts and neo to collect the result. In contrast, Para systems Smith require at least append as a library function. Let's look at the 3 list reversal examples closer. The following is one solution to the list reversal problem found by Param, which roughly corresponds to the following Haskell program, with the inner loop appending an element to the end of the list, a list accumulator. The following is another solution found by Param, which roughly corresponds to the following Haskell program. This time, the solution uses the inner loop to append an element to the end of the resulting list. Finally, the following found by Para utilizes continuation passing style to encode top-down traversal. This is enabled by supporting using a function as an accumulator type. This roughly corresponds to the following Haskell program. Judging from the performance of our system, it seems that we must be doing something right. It turns out that its success depends on a few design choices, including the use of paramorphism. However, once we figure out the right thing, the algorithm is pretty robust and is able to solve many different problems. I'll now walk through this approach we are using. Our targeted language is a standard, simply typed functional language. The first ingredient of our synthesis algorithm is a stratification of the language syntax into templates and holes. A template is an incomplete program with multiple typed holes. For example, the following is a template, which gives a correct list appended function if all holes are filled in appropriate terms. The Para combinator enables primitive recursion, which I will explain later. For the time being, let's note that the template defined the shape of the recursive program and introduces a number of variable bindings, which can be then used inside the hole. While we basically allow arbitrary targeted language construct to appear in the template, we restrict the syntax of the terms to be filled in holes. In Para, holes can only be filled with a first-order subset of the targeted language, which are just applications and constants. Neither recursion nor variable bindings is allowed to appear in whole terms. This turns out to be crucial because it makes the search space for whole terms much more well-behaved. Essentially, whole terms are just straight-line code, a problem with stochastic synthesis has previously been applied successfully. So a little in detail, the template introduced recursion via the paramorphism combinator, which is the second essential ingredient of our algorithm. The third ingredient is to employ stochastic search technique to solve for whole terms. The search procedure itself is embarrassing in parallel, in stark contrast to any previously deduction-based systems. This is made possible by our stratification, which simplifies the syntax for whole terms which we need to search upon. Condition the search space of whole terms to be well-behaved. Our approach shares similarities with program sketching, which allows programmer to specify incomplete prompt for synthesis. Our motivation privately focuses on conditioning the search space of whole terms so that stochastic search becomes effective. We use a fixed set of systematically generated templates. This is a high-level overview of our synthesis algorithm. I will now go into some more detail. First, paramorphism. Paramorphism is an instance of recursion schemes, which are just canned recursion patterns. It has been advocated in the functional programming community because it handles the hard part of writing correct recursion patterns on data types, and the program just needs to write non-recursive logic. Paramorphism, or fold, is a simplest example of recursion scheme. When acting on list, it is just a plain old write fold. The fold combinator accepts a list, an initial state value, and the function that takes a list element, a state value, and then produces a new state value. The fold combinators then iteratively apply the function to the list elements in bottom-up order and returns the final state value. Paramorphism is a generalization of fold, which gives function f access to not only the element at the current list head, but also the list tail. Note that I'm writing everything specialized to list here, but paramorphism, like other recursion schemes, can be extended to arbitrary algebraic data types. A fully general way to write it would require the use of functor fixed points, which I omit here. An example of paramorphism is factorial. In that case, we are dealing with natural numbers rather than list, but it's very similar. A fold over a natural number is just to loop for n times, and the paramorphism gives the loop body access to current iteration count. It is impossible to write factorial as a catamorphism over just natural numbers without using tuple types, but straightforward to write using paramorphisms. In the current Para system, we focus on templates in the form of properly nested paramorphisms as a generalization of proper loop nest. It is straightforward to extend the set of templates to include, for example, several sequentially chained proper recursion nests, but a single proper recursion nest is already expressive enough for all of the benchmark. As we have seen in previous examples, the paramorphism combinator can have different instantiation when it recurses on different type of structures, say list or natural numbers, and different state types. This results in some degree of freedom, even if we settle on a propagation nest as the overall shape of the recursive program. Therefore, we write a code generator that initiates a template given the state type and the list of types to recurse on. For example, we get the following template that uses list of natural numbers as a state type and recurses on a list of natural numbers and a tree of natural numbers at recursion depths 1 and 2, respectively. Note that we're recurring on a non-recursive type, such as Boolean, the paramorphism will degenerate into a pattern match. We then use an outer loop to enumerate combinations of state types and recursion types and run the inner loop, which is the stochastic synthesis for whole terms on all these templates concurrently. Now let's talk about the inner loop. The goal of the inner loop is to fill in holes in the template to produce a correct program. Note that the whole terms are non-recursive and are essentially straight-line code. We use a guided stochastic search for this task. First, we have a cost function measuring quality of entire programs. At each step of the search, we apply a single step of rewrite of mutation to the non-recursive whole terms in our candidate program. Different kinds of rewrites include substituting any subterm with a variable and adding or removing one layer of application. We specifically accept the proposed new candidate program based on our cost function. The cost function consists of two terms. One measures the size of the candidate terms, and the other measures the correctness of the candidate terms. The constant alpha sets the weight of the two contributions, and we set it to 1. The correctness term is computed from the added distance between the actual program output or example input versus expected example output. Finally, let's end the presentation by looking at an example of our search algorithm running in action. We'll look at this template generated from our appropriate nest generator. It is a single level of paramorphism over list data type. At the beginning of the search, which is point A, each hole is initialized with its default candidate. In this example, every hole has type list of natural numbers and is initialized to nil. This initial function also returns nil, regardless of input. The first significant decrease in the cost function occurs after fewer than 10 accepted proposals when the term in the second hole is rewritten from nil to L2. We now have a function that always returns its second list argument. This function has the lower cost because the second list is more similar to the desired output, which is a concatenation of two lists. The search discovers this function at point B. The next significant better function is found at point C. This program iterates over L1 and adds a constant 0 to the ahead of the result for every iteration. This function has a lower cost because its output is even closer to the desired output, with the correct length but potentially correct element in the final list. Finally, we discover the correct append function at point D when we change 0 to a variable h in scope, which is the element of the first list. In summary, we have developed a new synthesis system which uses stochastic synthesis to fill in holes in paramorphism templates. The system can handle nested recursions thanks to the use of recursion schemes and can synthesize surprisingly involved programs with very little prior knowledge. We use paramorphism templates to reduce the problem to synthesizing non-recursive terms so that stochastic synthesis can be effectively applied. Thanks to the use of stochastic synthesis, the algorithm is also embarrassingly parallel and can make use of today's increasingly massive computation power. Finally, our code is available at the following address. That's the end of my talk. Now, questions and comments.
Thank you.
Check. Hi, thanks for the excellent talk. So I have a question about the cost function part. So it seems like in the cost function, there is an added distance, right? So do you require that the output to be structural? For example, the inductively defined natural numbers. So what will happen if the output is just a natural integer, native integer in languages?
Yeah, good question. Let me find this.
Yeah.
Yeah, so it is defined formally defined by regarding the algebraic data type as a labeled trees and computing the added distance. But for natural numbers is a very good example. So when you represent it as a machine integer, there's an efficient way to compute the distance, which coincide with the formal definition. The result is just the absolute value of the difference of the two natural numbers, right? Because the natural number is when represented in unitary, the tree of depth n. The edit distance is exactly absolute value minus m for n and m. Yeah, so the system is extensible, and we formally define the cost function as edit distance, but you can supply your own edit distance function when you have some like some black box types. Does that answer your question?
Hi, thanks for your presentation. It seems like really awesome work. I was really curious, did you run an ablation on your, I guess, stochastic synthesizer versus something like a bottom-up with observational equivalence to see how much benefit you get from that approach? It seemed really interesting.
Oh, yeah, exactly. So in the paper, we tried to change the stochastic synthesis with, I think we can let the result here. In fact, the second column is when we change the stochastic synthesis part to using a bottom-up, actually using a best first search, guided by some cost function, but deterministic and in theory have a better theoretical guarantee like completeness. But when running in action, we see that stochastic synthesis show like significant advantage over that, and we have some motivation of like that's an idea of why happening in our paper, and basically stochastic synthesis it is possible to like because if you're using best first search, which is a greedy approach, then even guided by cost function, and it will be more difficult to make change to the program that will require at least 2 edit in different places to make the overall cost function reduce. But it has a non-zero probability for the stochastic synthesis variant. Yeah. So in summary, basically, we tried a deterministic approach and compare it with the stochastic synthesis variant, and it seems that stochastic synthesis variant do have some significant advantage. Does that answer your question? Thank you.
Sort of, I think the complementary question to that, which is that when you use a edit distance sort of a cost function, you're kind of assuming that you can get closer to the solution, and that depends on the cost function, naturally leading downhill towards the correct thing, but not that cost function might not always be available. The edit distance, only some problems would have that structure, I would think. Have you run into synthesis problems that you just can't solve because that cost function just doesn't lead you to the solution?
So for the problem that we tried, which are all defined using algebraic data types, the cost function is pretty effective, and I think we also have some motivation for what that is the case, because when we limited, like say we ignore library functions for now, and if we limited the whole terms to be just constructor applications, then edit distance exactly measures the distance between 2 execution traces, right? Because the only way you can construct the value is to apply constructor application, and then the difference in the program trace that lead to this value are exactly the edit distance when you regard the output as labeled trees. Yeah, so that's the motivation, that's the intuition, and also in practice it turns out to work pretty well for at least problem defined with algebraic data types. And that's basically what I have to say.
Thank you. Thank you. Thank you for staying up late. Oh, sorry. No one more question. Yeah.
I was wondering if you tried comparing against burst empirically.
Yeah. It's also included in one of our. Oh, actually, we didn't include it in our comparison. We haven't compared it empirically. I think our reason for that was basically when we look at burst, it seems to be working on an imperative language, which is quite different from what we're working on, because everything we work on are purely functional. Yeah, so we haven't did that comparison.
Burst doesn't work on an imperative language; it's a functional language. But anyway, I was just curious. That's all.
Okay. Yeah, we did include it in our related work. Yeah, but we didn't include it in the evaluation.
Thank you. Okay, let's thank our speaker again.